Hello, this is Mr. Craig, and I want to talk about salts today. We talked earlier in the year about strong salts. Today's a great opportunity to talk about weak salts. So we'll start off with solubility equilibrium and solubility product. Up to this point, again, we've talked about strong salts and strong acids, strong bases, and the thing to recall or remember about strong acids and strong bases is that they dissociate 100%. So the things that we're going to be talking about today are salts that do not dissociate 100%, and one way to know that you're looking at, say, a weak salt is that you have to know your solubility rules as we get closer and closer to the AP exam, depending on where you're at in the class right now. Knowing the solubility rules is paramount to succeeding on the AP exam. So make sure that you know your solubility rules, and also realize or recognize that if you're looking at a weak salt, you know that you're looking at a weak salt because you'll have some K value. So we're going to talk about weak salts today, and weak salts are simply that. They do not dissociate 100%, and they're considered to be not soluble under the terms of the solubility rules. So let's see. I don't see anything that's really phenomenal there, so let's jump right into the example. And again, this is very, very similar to a past AP exam question, but again, it gets us back into working with ice charts, K values, equilibrium, and again, the first question on the free response section of the AP exam will always be an equilibrium type question, and this type of question was question number 1 for 2010. At least on the A form. So let's look at the example. It says silver sulfate dissociates in water according to the equation below, and then it gives the balanced equation right here of the dissociation of that. And do recognize that we are looking at a weak salt because number 1, solubility rules, but number 2, we have a KSP value. Now the KSP deals with the solubility product, but if you want to think of it as a salt product, I tell my students that, and that's okay. You can think about that as being a salt product. So it's going to be a weak salt. Alright, so we want to write the expression, and again, reviewing how to write expressions, it's always products over reactants. So KSP is equal to the products, and again, here are our products. So we have our ion. We never include solids or liquids, so silver has a +1 charge. Since it has a coefficient of 2, we want to square that. And also the other product in this case is sulfate, and it has a -2 charge, and it has a coefficient of 1. Now, we don't put the silver sulfate underneath here because, again, that's a solid. How do we know it's a solid? Look at your the phase designation there. So we're done with our part A. Now, some of us might say, well, we're not quite complete yet until we actually put the value, and that's fine. If you put that on there, that's great. If you don't, hey, nobody's going to lose any sleep over that. But again, make sure that you're showing this part. Okay. All right. Part B, calculate the concentration in molarity, which is moles per liters, of silver ions in a saturated solution of silver sulfate. Now, again, we're looking for the maximum amount that will dissociate in whatever volume it is. So again, we have our balanced equation, which is given up above, where we have silver sulfate, and some of it will dissociate. Oops, let me erase that. Just going to put the coefficient in there. So we have 2 silver ions, and we have a sulfate ion. So again, we're going to be looking at an ice chart. Now again, I like using ice charts simply for organizational purposes. You'll never ever be graded on an ice chart, but again, it'll help keep you out of a lot of trouble. So since it doesn't say anything about how much we start with, 0. Also, realize that over here we have solids, so we put dashes there. Never put 0 for a solid or a liquid. A dash means nothing's going to change. Pure solids, pure liquids, never change their concentration in an equilibrium reaction. So on the product side, these will increase by a factor of x depending on what coefficient they have. So for the silver it'll be by 2x, for the sulfate it'll be by x. So we'll have our 2x and x. And again, this is for organizational purposes. So now we can go back and look at our equilibrium expression here. Okay. So looking at the equilibrium expression, now we're going to plug 2x in to our expression there and x in for our sulfate. So again, our KSP is going to be 2x squared times x, and again that's all equal to 1.2 times 10 to the negative 5. Okay. Which, if I take 2x squared, that's 4x squared times x is 4x cubed. Okay, we want to solve for x here, so x cubed, and I'll show it stepwise here, is 1.2 times 10 to the negative 5 divided by 4, so we're going to bring the 4 over, which gives us 3.0 times 10 to the negative 6. Now again, you would want to use your calculator on this, and then to find x, actually let me see if I can get more room here. See if I can get some room here. We're fine. So we can calculate what x is by taking the cube root of our value here times 10 to the negative 6, and let me type that in real quick. And some calculators are kind of nice. My little Casio here is allowing me to do cube roots. 3 negative 6, so I get a x is equal to 0.0144. Now that's molarity, and that's what x is equal to. Now unfortunately silver is 2x, so when we look for the, I'm going to put it over here, silver, concentration of silver is equal to 2x, so 2 times 0.0144, and so silver is equal to 0.0288, and that's molarity. Okay, sorry about running out of room there. Alright, let's look at part B. Calculate the maximum mass in grams of silver sulfate that can dissolve in 100 milliliters of water. So we calculated x as being 0.0144, and so we know that x, if I have one of these, I produce one of those, so we know our concentration. So we'll start off with 100 milliliters and convert that to liters. Oops, I'm trying to keep this under 10 minutes so I can post this on YouTube. 0.0144 moles per liter, and then 1 mole of silver sulfate is equal to something here. So whatever the molar mass of that is, oh boy, I better hurry, got a minute and a half. So 2 times 107.87 plus 32.06 plus 4 times 16 is 311.8 grams. That's the molar mass of silver sulfate. Multiply that times 0.0144 times 0.1. So I can get a maximum of 0.4, we'll say 49 or 45, somewhere around that ballpark of grams of silver sulfate. Now that's not a whole lot that can dissociate, but again, it's a weak salt, so we wouldn't expect to be able to dissociate very much. Alright, I'm going to make part 2 of this to discuss a common ion effect, and that should be a really good discussion with a lot of concepts. So tune in to part 2.